All right, so continuing from where we left off, right? Calculating a limit as x goes towards either infinity or negative infinity. And what does that essentially mean for the function, right? As it goes off in those directions towards the left side or the right side forever. And we said that it's very similar to asymptotes. Oh, Joe, thanks. You are here. That's strange. Yeah, that's weird. Why doesn't it record you? Thanks for typing that in, Joe, so I can actually... And my program must be bugging a little bit. So thanks for typing that in the chat, so that way I know that you're here. I can mark you here. All right, just double checking, just in case it is messing up. So if it's messing up for Joe, Ilias, are you here? And Chris and Diana, if you're here, can you just type something in the chat so I know that you're here? Thank you, Joe, for doing that. I might have to adjust this attendance app. All right, anyways. So we were saying, right, it approaches this number as it goes off towards infinity, and we call that the asymptote. Specifically, it's the horizontal asymptote, right? Now, we also talked about you were lied to when you first learned about asymptotes, right? Well, at least maybe actually you weren't lied to. I don't actually know. I wasn't your teacher or not, so I can't assume this. But I know that when I taught it, I accidentally lied to my kids. I told them an asymptote is this imaginary line that a function can never cross and can never touch it, right? And that's actually half true, right? It's only true for half of the times, or maybe less, or actually maybe more. But for a horizontal asymptote, right, you have something like this for 1 over x. It looks like it's always true. It looks like as I go towards positive infinity, this thing will get closer and closer and never quite touch y equals 0, right? And that's because as I make x larger and larger, right, that's what infinity is, right? It's going to like 1 over 100, and then it goes over to 1 over 1,000, right? And then somewhere down the line, it's like 1 over 1 billion, right? 1 over 1 billion isn't actually 0. It's just really, really small, getting really, really close to 0 and never quite reaches it. And as I go off further, 1 over 1 trillion, 1 over, I don't know what's after a trillion, 10 trillion, right? 100 trillion. It's getting closer and closer to 0, but it doesn't touch it. And that's the idea of this limit, right? What is it approaching, right? It's not what the function value is at infinity. We don't know what that is. We can't calculate that. But we can see that as the limit approaches infinity, right, the function approaches 0. And that's the key factor of what a horizontal asymptote is, right? It's what does it approach, right, as it goes off in those things. And we learned that as end behavior as well. So you'll say, well, yeah, if we go by definition, then I can never see when a function is going to cross that horizontal asymptote, right? And there is one example of this, and I wanted to show you before we actually go on. Where are you? Here you are. So let's go ahead and take a look here. I want to show you this function real quick, just to give me a look at it. So let's have a function here. It's x times sine of 1 over x. Right? X times sine of 1 over x. And if you did the homework, you should recognize this problem. If not, you'll see it in the homework when you go in there. You weren't actually asked to find the limit as this goes towards infinity in the homework. It was that you were asked to find it as it goes to 0. And one of the things you're supposed to see is if you do it graphically, right, you can kind of see like what's happening here at 0, and it's just kind of neat to see. This thing goes pretty crazy as they get closer and closer to 0. But you can actually see it graphically that it's approaching 0 as x approaches 0. But that's not the cool thing I want to show you today, right? Although I still think this is cool. If you just keep zooming in, look at this. You'll start to lag, though, if you do this, but it's just fun to do. Anyways, let's get back out here. So what I'm saying is what happens as this thing goes off towards infinity, right? Wait, did I pick the wrong function? I think I did pick the wrong function. Was it x sine of x, or was it sine of 1 over x? Sorry, hold on a second here. I forgot the function already. No, might be mistaken. Was this one? Ah, yes, it was this one. Sorry, it was sine of x over x. Sorry. Wrong function. I just remember the other function because it was cool when you zoom in. It was another neat one to do. But let's go back to this one. Sine of x over x, right? So check this out. as this function is going off towards infinity, as I'm going towards the right side of the graph, can you guys see that it's weighting up and down right here, but it's approaching the same number, right? It's getting closer and closer to 0 as I move along, but it does actually hit 0 and passes through it and goes into the negative side, right? But this is still considered a horizontal asymptote when you look at this thing, right? It's getting closer and closer to 0, and it passes through it, but as it goes off towards infinity, it'll just keep doing that. So this has a horizontal asymptote at y equals 0, but it does touch that asymptote. It actually crosses it over and over again. So for a horizontal asymptote, we're no longer just defining it as, oh, it's an invisible line that your function is getting closer to but not touching. But we're just going to say that it's an invisible line that your function is approaching as you go towards infinity or you go towards negative infinity. Okay, so just keep that in mind. And it's like, oh, so an asymptote it can touch it? And yeah, for a horizontal asymptote, it can touch it, not only once, but infinitely many times, even before it gets to infinity. It can cross it multiple times, but it's still just what it's doing is, if you can imagine it, right, it starts off like wide like this, but then it gets smaller and smaller and smaller and smaller and smaller and smaller. And it's still doing this. It's still kind of like vibrating back and forth really quick, but it's still crossing over. And it's still trying to approach 0. It just doesn't quite reach it, right? Anyways, that's just something to keep in mind now. So hopefully that you'll see that when you're talking about horizontal asymptotes, right, it's not the same as what you might have been taught in the past, where it's just this invisible line that it never reaches, right? It's approaching it, right? That basic concept of your limits here. All right, I'm talking too much about that. So let's go on here. The next thing that we're going to talk about is, well, how do you calculate these guys, right? In the other ones, when it was x is approaching a specific point, right, we had these 3 rules that we were trying to follow: graphically, numerically, and analytically. I'm going to change that. Algebraically. Gotta sound that out. Algebraically, right? Analytically, algebraically, you get the idea. So looking at this one, let's say I was looking at it graphically. Well, you just graph the function. If you know your parent graph, and I was looking for example, 1 over x, right? And I know the parent graph of 1 over x looks like this. I know that there's one horizontal asymptote, and that one horizontal asymptote applies in both directions, both in the positive infinity and the negative infinity. And that's just based off looking at the graph, right? Second thing is maybe we can try looking at it numerically. And that's what I was doing right here, numerically, right? I was making a table of values, right? And the values were if x was equal to something and f of x was my 1 over x function. And I was, typing in like, what's the output value at 100? Oh, it's 1 over 100. Oh, what is it at 1,000? Oh, it's 1 over 1,000. Oh, what is it at 10,000? Oh, it's 1 over 10,000. So the idea is you can still do this table, but now you're not approaching a point. As it goes off towards infinity, what I want you to think is start to imagine really large numbers, right? Like ridiculously large, like so large that it's like you can't even comprehend it. Like, I don't know, like a billion. That's all I could think of right now. I wanted to say something insensitive, but I'm going to hold back because I'm recording myself and I don't want any record of me saying anything insensitive on recording. So yeah, something really large, right? So that's for that one. Now, how would we do this one algebraically? Well, we wouldn't actually necessarily, well, I guess we could just look at the function algebraically, right? We can say, well, what does that function 1 over x tell us, right? And hopefully you guys will understand that, well, if we're dealing with a rational function like 1 over x, right, there's some rules that we have to abide by algebraically when it's a fraction, right? And you hopefully would see that, oh, if I were to plug in the domain 1 over 0, right, I get something that's undefined. So at 0, something funky is going on there, right, for x equals 0. And then you can see what the range values are. And that should show you that the range, this thing could never equal to 0. So therefore, there must be something going on there. And then you'd have to go into further, investigation. All right, let's just take a look at this one right here. Let's take a look at this one. what is the equation for the horizontal asymptote for y is equal to 2 plus 1 over x? So again, if you were to approach this from one of these three ideas, either graphically, numerically, and algebraically, right, it takes a little bit of knowledge beforehand if you want to do it graphically. So let's say I was looking at this graphically, right? 1 over x is my parent graph, so I know that my parent graph looks something like this one up here, which is going like a little shape that's like this, right? But that way and that way, with a horizontal asymptote here, right? So what could I do then is realize that this notation right here is very similar to f of x plus k. If you guys remember that, right? That plus value outside of your function is a vertical shift. You guys remember that? If you had it inside the function, it'd be a horizontal shift. If it's outside the function, it's a vertical shift. And this applies here. This 2 is like your plus k. And what would that essentially do to your graph over here? Well, it would just take that, right, the same shape that you have, and then just move everything up 2, right? So instead of having a horizontal asymptote at y equals 0, which is the case here, it will now move it up to y equals 2. And then your graph would then now look like this instead, which is still the same, but everything's just shifted up. So just thinking about it graphically and visualizing that shift, you could visually see the shift for that horizontal asymptote equaling 2 now instead of 0, because you just moved it up 2, right? Hopefully you guys are able to see that. If that doesn't help you out, you can look at this numerically, right? Again, you can look at this numerically. If you're looking for the horizontal asymptote, right, by definition, that's basically saying look for the limit as x approaches either infinity or negative infinity of 2 plus 1 over x. And again, you just start plugging in numbers in for x, right? You can just start plugging in numbers. So this is implying that what is this function approaching as my x approaches infinity? So I can try it for 2 plus 1 over 100, for example, right? And then I can try it again for, let's see here. This is for if x was equal to 100. We could try it again for x is equal to a very large number, like a million. And I can see that that's going to equal to 2 plus 1 over a million, right? And I'm hoping you guys are seeing what happens here. Just like I did up here when I was doing these numbers for just 1 over x by itself, right? Like 1 over a billion, for example, is getting closer and closer to 0. Okay, it's getting closer and closer to 0. So what essentially is going to happen is, as I get off towards x is equal to infinity, which by the way is you shouldn't say that because it doesn't mean anything. X, what does x equaling to infinity mean? You can't actually have it equal to that, right? Infinity is not a number. So I should say as x approaches infinity, right, this 1 over infinity thing is essentially approaching 0. And what that entails is if that is approaching 0 and it's still being added to 2, right, then I can say that the limit, I'm writing all over the place here, I just realized, as x approaches infinity of this function of 2 plus 1 over x, I can make that claim that this is equal to 2. It's just equal to 2 plus that 0, right? So that tells me then if I find the limit as x goes off towards infinity of this function is equal to 2, that tells me that the horizontal asymptote of this function is y equals to 2. You guys okay? This is a weird thing to go over right now, and I want to check in with you guys. Does that kind of make sense? If it's all too much, you can just stick with it graphically for now, right? Visualize the graph of the function and see what it's doing that way. And that's a good way to start. Graphically helps with a lot of people. The next step is after you get it graphically, try looking at it numerically. Try plugging in the numbers and seeing what occurs there. So you can see like, oh, as this x goes towards infinity, like it gets bigger and bigger. If I had something like 2 plus 1 over infinity, I'm hoping that I can imagine myself seeing that this function right here, as it starts going towards infinity, is just going to approach 0. Okay? It doesn't mean that it equals 0, right, guys? I'm not saying 1 over infinity is equal to 0. I'm saying that it's approaching 0. And that's what we care about when we're looking at limits, right? The limit is just the value that your function approaches. So, yeah. Okay. How you guys doing? I know it's a weird concept to grasp, right? But limits that's the power of a limit, is you can now look at these things approaching without having to worry about what is it actually equal to. And we did that when we were approaching a specific point, right? Now we're doing it as it approaches infinity, right? Off towards the left and off towards the right. I can do the same thing, by the way, as it goes off towards negative infinity. If I was looking at 2 plus 1 over negative infinity, and it's the same thing. 1 over negative infinity is just this upside down part right here, and it's still approaching, right? It's still approaching 0. So this guy is still approaching 0. So if I was looking at the limit as x approaches negative infinity instead of positive infinity of this function, right, this thing is still approaching 0. So this would still come out to be 2. So I have a horizontal asymptote at y equals 0, and it applies to both positive infinity and negative infinity. Okay? All right. Let's take a look here. I got two functions here. Yeah, I got two functions. Okay, first function up, f of x, right? And I'm looking to see what is the horizontal asymptote for this one. Anyone got any ideas? What's one way we can do this? What's one method? Type it in the chat. What's one method we can do for this one? What would you like to attempt? What instinctually do you feel like you need to do? Are you guys here? Is my chat frozen? Simplify the equation? Yeah, that's a good instinct. That's a good try. But even with my algebraic abilities, I don't think I can simplify that, because x squared plus 1 can't factor. But if I could simplify it, I would try that. That is definitely a good way to start, right? So let's take a look at this, guys. I'm looking to find the horizontal asymptote, and by definition, right? By definition, that's basically just asking for me to find what's the limit as x approaches infinity of this function, and finding what is the limit as x approaches negative infinity of this function, right? So how would I calculate that? How would I calculate what are the three techniques that I've shown you guys to help you to calculate a limit of a function, right? What are the three techniques? You want to give me one of them? Just type it into the chat. What's one of the techniques that we should use, or that we could try to use at this one? Graph it. Yeah, Monica, that's great. That's like the perfect way to start off a problem if you don't know it, right? And you know, if you're not in a section where it's a non-calculator part and it is a calculator, just try graphing it on your calculator, right? Let's just see what it looks like. I'm going to go ahead and open up my calculator right here, right? And I'm going to clear out the stuff that's there, and go in here and clear out what's in here and type in this function. Have you guys gotten pretty good at using your TI calculator yet? Right? Again, if you have an Android, right, download WabbitEmu. If you have a iPhone, I don't know, I was drawing a blank on that name. If you have an iPhone, I believe it was Calculate 84 was the name of the program that you guys should try, or there was some other ones. I forgot them already. But if you guys are who are on iPhone and you found one, can you type it out into chat? One that you have been using that works really well, and let your fellow classmates know what's a good program that you guys have on your iPhone that emulates this, right? So again, if you have an Android and you haven't looked this up yet, WabbitEmu, it's awesome. All right, so I'm gonna go ahead and type in this function here. F of x is the same thing as my y function in this case, right? So I'm gonna go ahead and say y is equal to x over, so I'm gonna go ahead and hit the divide button, and it's the square root function. And for you to find the square root function, it's right there over the squared function right here, but you see how it's in blue? So you have to hit the blue button and then hit the squared button, and it pops in the square root for you. And then I can go ahead and hit the rest of this, which is going to be x squared plus 1. And that's the graph, right? That's the equation right there. On the TI calculator, after you enter it into y equals, you simply go to the graph. Oh, whoops, hold on. I forgot to adjust my window. So yours would default to 0, 0. This one I used it earlier and it was zoomed in on something. So if you ever need to fix that, like you were zoomed in on something and you don't want to be there, you can just hit the zoom button in the middle here and press 6 to go back to standard. So when you hit that, it goes back to standard view. And this doesn't really help me too much, but you can kind of see it, right? It's like this shape right here. It's like down here, and then it comes up to 0, and then it goes up here. So I'm going to zoom in a little bit more. So again, I'm going to hit zoom. I'm going to zoom in, and it's focused at 0, 0. That's a good spot. I'm going to go ahead and zoom in there. And that's what the graph looks like, right? That's what the graph looks like. Yeah. I can adjust the window as well, guys. If you click on window here, you can adjust what your X min and X max is. It's just like in Desmos. You can adjust your window size. So I can make my X's, let's say, go from 10 to 10. Or I'm sorry, negative 10 to 10. Right? And then I can make my Y values. Let's say, it looks like it needs to be a little bit closer. Let's go like 1.5 instead of 2.5. And you don't have to do this, by the way. This is just practice for you to adjust your window, and it's good practice to do, just to see how you can adjust it. And when you adjust it, it makes it a little bit more clearer, right? You can actually see this now. And graphically speaking, are you guys able to see how many asymptotes are you how many asymptotes do you think you see here? How many asymptotes do you think there are here? 2. That's right, Monica. That's 2. Right? It looks like there's 2 asymptotes in this problem. Yeah? And those 2 asymptotes look like, well, one is at the top right here at 1, right? And the other one is down here at -1, right? So graphically speaking, right? Looking at this graph, I see 2 horizontal asymptotes. I see one at y is equal to 1, and I see another one at y equals to -1. Yeah? Not too bad, not too bad, right? And that's what I would say if I was just doing this graphically and they were asking me to find the horizontal asymptote, I'd just stop there. Right? Now, let's say I was in a portion where I couldn't do this graphically. I had to do it some other way because they blocked the, they don't have a graph. I don't have access to a graphing calculator. Or not a graphing calculator. I don't have access to the graph. So another way I can do it is if graphically doesn't work, what's another way, guys? Tell me. If graphing doesn't work, what's another approach we can use if graphic is out of the question? Numerically. I like that, along with the 980I9. Numerically, Max, you're right. Numerically is another way. Monica, I see yours as well. Yeah, numerically is another way that you can do it. So I would make a table. Now, here's the thing, though. Do you know what values you need to plug on your table when it's going off towards infinity now? As x goes towards infinity and x goes towards negative infinity. I hope you realize you're not going to be going like 0.1, 0.01, 0.001, right? I'm not approaching 0 in this case. I'm approaching infinity. So for your table now, you need to start thinking of very large numbers and seeing what it's going off towards, right? So you want to think of like maybe 10, 100, a million, right? Now I'm supposed to make a table. I'm just going to cheat here just because sake of time. But I'm going to go here and press second and hit table. And here what you can see here is a table that calculates the values for you for whatever x's you want. And right now it's defaulted to just go by 1s, right? So at 0, the function's equal to 0. But as I keep going off towards positive numbers, take a look at what's happening here. At 1, it's 0.7. At 2, it's 0.8. At 3, it's 0.94. At 4, it's 0.97. And then it goes to 0.98, 0.98, 0.98, 0.99. I'm not even at a large number yet. I'm not even at like 100 or I'm not even at 100 yet, but I can already see as I'm increasing my x values, right? You notice the y value is approaching 0.9, 0.99, 0.9999, 0.9999. You get the idea. As I'm going off towards infinity, right? As I'm going off towards infinity, I can say that this function, it looks like the limit as x goes off towards infinity, the function, the limit is approaching 1. And then I can do the same thing towards negative infinity. So I can go back the other way. By the way, you could do all this on Desmos as well. If you want to make a table, I can show you guys that. If you guys stop by my office hours, I can show you how to do this on Desmos. If you aren't comfortable with downloading an app that you're unfamiliar with, Desmos works this way as well if you want to do it for your homework or just for your own practice, right? It never hurts to practice. But look, as I go off towards negative infinity, this is going to negative 0.99999 forever now as I go off towards negative infinity. So the limit of this function as it goes off towards negative infinity is not approaching 1, but in this case, it's approaching -1. It's approaching -1. All right. So those are two ways that you can approach these problems, right? Graphically and numerically. The last way is algebraically. And algebraically sometimes is really like just more satisfying, I'd say. At least for me, it was more satisfying because it was something I was familiar with, right? Like something we saw from before that we've been doing for the past 3 years. You've been solving things algebraically for so long, and it just feels comfortable to do. But this one is going to be a little bit outside of the box when you try to look at it this way. And it comes to this, right? That plus 1, if you're looking at this as x approaches infinity, that plus 1 doesn't really come into play anymore, right? Because when I go towards infinity, you're only looking at really large numbers for x. And as I get to really large numbers for x, the plus 1, it's still adding 1, but it's very like insufficient, right? It's very, very small, very minuscule. Yeah, so when I look at this, essentially what's occurring here is what I'm focusing on is just x over the square root of x squared, right? The plus 1 is there, but it's just going to make it a little bit messy, right? But as I go off towards infinity, this is what I really want to focus on. And when I really focus on this, right, algebraically speaking, just looking at the square root of x squared, right? Can anybody tell me, what does that become? What is the square root of x squared? Any ideas? What does the square root of x squared become? X. And Sydney, X. Brian, Sydney, you guys are halfway right. You got half the answer there. You are halfway there. The square root of x squared, yeah, x is half of it. No, not x squared. The squared goes away when you square root it. But no, we got that. I was just talking about the bottom part, right? What is the focus here of the square root of x squared? It's not just x. It's not just x. That's half of the answer. X to the first. Eva's got it. Eva's got it. It's plus or minus x. Yeah, the negative x, Gracie. That's right. Right? When you take a square root of a variable, you need to include the plus or minus part. So when I simplify this square root with this squared, it technically comes out as plus or minus x, which then hopefully you can see algebraically speaking, as this thing goes off towards infinity, x, you end up getting x over positive x, and you end up getting x over negative x as your two possibilities. It's this one or that one. And when you have that, you have your two equations, which is going to be equal to 1 or negative 1, which is what we got for our answer here when we were looking for a horizontal asymptote. Now, is it always going to be this technique when you do it algebraically? Goodness, no, right? No way. It will never be this. Actually, I'm going to say, no, I shouldn't say never, but it will rarely be the same thing that I show you as my examples, right? Rarely will that be the case in your calculus class now, right? And it's kind of like a little frustrating, but that's just, you got to realize that you're going to have to use some algebra skills that you haven't used in a while, and you hopefully can use it to apply to these problems. And again, if you can't, don't fret over it. Don't feel bad over this. You have two other techniques, which is graphically and numerically, okay? Your goal is just to get these answers, not to do it this specific way, right? You need to get over that fact of like, well, it's not working for me this way, and this is the way I've always done it, right? You want to go beyond that and just have different methods of getting to your solution, right? You don't have to focus too much on that. Can you guys right now either open up Desmos or open up a graphing calculator or make a table, and can you guys try this problem right here? Can you guys tell me what is the horizontal asymptote for this function right here? Go ahead and give this one a try. This one should take you no more than I'm gonna set a minute and a half. I'll set it to 2 minutes. I'll set it 2 minutes. 2-minute timer on this one. Go ahead and try this problem for g of x. Tell me what is the horizontal asymptote for g of x. And I'm gonna go ahead and set up a whiteboard for you guys to give me the answer. You can type it. I just typed it in there. Height. Get out of here. So I'm gonna go ahead and set up the whiteboard. So you guys go ahead and try to find out what's the horizontal asymptote equation. By the way, for horizontal asymptotes, I hope you guys understand why it's written as y equals, right? That's the horizontal line. So when I'm looking for a horizontal asymptote, I'm looking for the equation for a horizontal line. So it's y equals, right? Just keep that in mind. Let me go ahead and set this up. All I want is the answer. You don't have to show the work for this one on the whiteboard. So I'm going to go ahead and do this, and I'll put the link into the chat for you. Oop, copy and paste. So whenever you get a chance, can you go ahead and type your answer into that? Wait, actually, no, what am I doing? No. You know what? Don't do the whiteboard. Don't do the whiteboard. Wait, why am I doing the whiteboard? I have you guys on Pear Deck, right? You guys are on Pear Deck right now. Are you guys still on it? If you guys still have the Pear Deck open, that actually might be better. So yeah, with the Pear Deck, give me a second here. Let's go with text. And no, I lied. I can't modify it. Yeah, just go with the whiteboard because I can't modify your Pear Deck. Sadly, it just says that question. I thought I could add a question to it, but I lied. So I'm gonna just end that Pear Deck because you don't need to be on there anymore. So let me go ahead and Period 3 Calc. And then do it on the whiteboard. Do it on the whiteboard. Let me put the link back in there. Oh, I should have set this up ahead of time, so I should have made the slides ready. And I just wanted the answer. Oh well. Makes me a little sad. So I'm going to go in this Pear Deck presentation. It is over now, so we're going to go ahead and exit it. And we'll close that out. And yeah, go back to this problem here. I just jumped all over the place. So take a minute, see if you can figure out what's the horizontal asymptote, and get the answer for me in the whiteboard. Just type out what do you think it is, y equals, and then that's pretty much it. Go in there, use your name, and yeah. I'll stop talking for a second here. Is the equation for horizontal asymptote. Yeah, I should have just did this over here, but okay. Looks like a couple of you guys were able to open the whiteboard link. I've got 11 of you in there out of the 34 of you that are in here. Out of the 34 that you in here, so a couple of you guys haven't gone in there. Yeah, it's no longer on the Pear Deck because I closed that out. So don't go to the Pear Deck link. Go to this link right here, which is the whiteboard link, and type out your answer for me so I can get you some participation points for today. Tell me, what do you get as this one? And some of you guys already have the answer in there, and that's awesome. And I should give you another problem if you already have the answer. You know what? Maybe I should. What's a good one? Oh, yeah, it's okay. Just I think we'll be okay. Get your answer in there, guys, for those of you who can. Who haven't, those of you who haven't. And yeah, we'll get going. All right. I have only answers from 2 of you. Is it lagging for you guys? Is whiteboard like struggling for a couple of you guys, or are you struggling with the answer? Because if it's lagging, yeah, it can be kind of annoying. So let's go in there. Oh yeah, don't forget to hit save. I should say that too. I have it so it's on slow mode for those because I realized that if I do that, it's a little bit better. So you can go ahead and hit save, and that will be a little bit better. Oh, I got 4 answers now. I got 4 answers. Okay, interesting. I like it. They went with limit as it goes towards infinity and negative infinity. That's good. Some people already have the answer of y equals, right? Y equals. That's good as well. I have about 7, 8 answers going. Good, good. So yeah, I want you to try this. I don't want you to wait for me to give you the answer. I want you to attempt this one. All right, see what you get as your answer. Okay. Still waiting on a couple more people. I'm gonna. Yeah, good, good. Okay, more answers are flowing in. All right. So I'm gonna go ahead and print screen this, or sorry, save this as a PDF. If you're still working on it, get an answer in, and I'll save it as a PDF again afterwards. Yeah, I'll save it again afterwards as well. So here we go. Whoops. Here we go. Saved, and let's go ahead and talk about this. All right, let's go ahead and talk about this. So hopefully you either looked at it graphically, right, and you saw that it's approaching something, and you looked at it numerically, and you saw that it's approaching something. And then if you wanted to try it algebraically, right, it's very similar to the one we just did. And that's the way I'm going to do it right now, right? I want you to take a look at this algebraically as well. So I'm going to go ahead and do it that way. I'm going to say, well, what is happening as the limit, as let's say it's going towards, let's say, infinity of x over the cube root of x cubed plus 1, right? And again, we're focusing on as x goes off towards infinity. And really, we're only just going to be focused on the x and the cube root of x then, right? Because the plus 1 is still there, but it's small. It's negligible, right? So I can look at this one right here and I say, well, what is this approaching as it goes off towards infinity? Well, the cube root of x cubed, right? When you simplify the cube root of x cubed, it just becomes x, right? It just becomes x. And in the top over there, that's still x right there. Now, why is the cube root of x cubed just x, whereas the square root of x squared was plus or minus x? And that goes down to, like I'm telling you, you got to know these rules, right? Different powers of your roots, right, affect your outcome. So if it's an even power like square root, fourth root, sixth root, and you take that root of a variable, that needs to include a plus or minus. But when you're dealing with an odd root, like a cube root, then the sign for whatever's inside there doesn't change. So if it's already negative, it can come out negative, right? So if it's an odd power like a third root or a fifth root, it still comes out whatever the sign is inside. So there's no plus or minus in this case. It just becomes a positive x when it comes out because it's already positive to begin with. And when you do that, this then says that it's approaching 1. So I have one horizontal asymptote at y equals 1. My other one that I should double check is as it approaches the negative side, as x approaches negative infinity, right? And I see what it does there. So same thing now, I'm going to have here x over the cube root of x, and that still just goes towards x over x, which is still just approaching 1. So it's the same horizontal asymptote. So I have that horizontal asymptote of y equals 1, and there's only one of them. So that's my answer for this case. It's not 2 horizontal asymptotes, it's just 1. Now graphically, let's double check that is correct. So I'm going to go ahead and graph that over here. So let's say I was graphing x over the cube root. You have a cube root button. Let's go functions. Nth root, there you go. I want it as a cube root of x cubed plus 1. And let's look at this graph. Right? We were saying that our horizontal asymptote is y is equal to 1, right? And let's make that as a nice dotted line so we can see that it is a asymptote. And let's make that red and make this one black. So there we go. So as you can see the graph, right? As I go off towards positive infinity, it does look like it's approaching this red dotted line. And I can zoom in and I can go further along here, right? And zoom in and see, hey, does it approach it? And it does look like it's approaching it, right? Yeah, it does look like it's approaching it. So it's doing that on the positive side, and it looks like it's doing that on the negative side as well. It's approaching, whoa, it's approaching 1 as well. It's okay, just come back when you can. But yeah, so the answer for this one, y is equal to 1. So hopefully you guys are able to get that, okay? All right, saving the whiteboard one more time, just for those who type in the answer a little bit later. And if you haven't done so, go ahead and make sure you put in something into the whiteboard, and I'll go ahead and save your results or your answers that way. All right. Okay. Come back over here now. Let's talk about the properties of limits at infinity. So if I was telling you that as x goes towards infinity, the limit as x goes towards infinity of f of x is equal to L, and the limit as x goes towards infinity of g of x is equal to m, this is just like the last section. I hope you see that, right? If I have the limit of these two functions approaching infinity, or the same value as I had earlier, right? Then I can do some properties, some arithmetic with those values. So if I were to, let's say, look for the limit as x goes towards infinity of f of x plus g of x, right? And I already know what these individual limits are equal to when they go off towards infinity. The results would also be the same. I would add the two of them together. So we saw that actually. I don't know if you guys, I'll put this back on the screen in a second here, but we saw that, right? If I had the limit as x approaches infinity of 2, and I had the limit as x approaches infinity of 1 over x, right? And we had these as two separate problems. The limit as x approaches infinity of 2, that, by the way, you can have a function equal to a constant, right? Just y equals 2, it just goes across like this. Well, this would then be approaching 2. Hopefully you guys would agree. And then if I looked at the limit as x goes towards infinity of 1 over x, that's just equal to 0, right? And what I'm saying is, if I wrote a function that combines the two, functions, which would be 2 plus 1 over x, and then I take the limit as x goes towards infinity of this, I hope you guys see that it just comes out the same thing as finding out what the limit of this function is, and then adding it to the limit of this function. And it'll work for other numerical operations. So not only does it work for the sum, it also works for the product. It also works for the difference. So if I had the limit as x goes towards infinity of f of x minus g of x, right? That's just equal to L minus m. The product, same thing. If I have f of x times g of x, if I can find out each of those limits, I could just multiply those values together. For the quotient, it would be the limit as x approaches infinity of f of x divided by g of x. This would be equal to L divided by m, given that m does not equal to 0, right? If m does not equal to 0, then this rule would apply here. Quotient rule has a little bit more issues with that. So last two here would be the constant rule. So if I had the limit as x approaches infinity of a constant times f of x, if I'm multiplying by a constant, then it's still equal to whatever the limit value is, but then you just multiply by that said constant. And if you're like confused as to what that is, if my function, let's say my f of x was equal to 2, and then I was looking to find the limit as x approaches infinity of, let's say, 3 times 2, right? Well, I know that this thing would be equal to 2 itself, and then you just multiply by the constant that's in front of it, which is 3. And it would say, oh, that limit is just going to equal to 6. And you'll say, well, why would you even do that when you can just look at this 6? And I'm just saying, this is one example of it, and it's something that applies when you go into more complex functions like sine, cosine, square root functions, and different rational functions. So just keep that in mind. And last but not least is the power rule, which is the limit as x approaches infinity of f of x being raised to a specific power. Let's say it's what are some good letters that won't be confusing? I don't know why I'm pausing on this, because it doesn't matter what letters you pick, but j over k, let's say jk. So this would come out to be as the limit value being raised to j over k as well. So if you have it to a specific power, and you know what the limit as x goes towards infinity of the function itself, you can apply the power rule to it on the outside. All right. So, whoops. What the? Okay, so I got about 20 minutes. Awesome. So we can keep going here. I was hoping to finish this up, but Whoops. Why do I have the answers there? Let me erase that. So let's take a look here. Right? It says you try. And you know what? Let's try it. It doesn't even, yeah, let's see if you can try to evaluate these limits. So go ahead and try these two. See if you can apply the rules that we did earlier and see if you can figure out what these values are. And if you guys could, I'm going to clear your whiteboards right now. So if you guys have that open still, go back and type in your answers for this. Let's number these, by the way. Let's call this one number 1 and this one number 2. And you can just give me the answers for these. I'm going to go ahead and clear your whiteboards. Oh, wait, you guys didn't start yet, right? No, it doesn't matter. I already cleared it. So go ahead and, sorry if I cleared it if you already started it, but go ahead and try these two. See what you get. What do you get when you are, I'm hinting at the next part of the lecture here. Let's go there. So see what you get when you attempt to find the limit as x goes towards infinity. I'm not asking for negative infinity, okay? I'm just asking for as x goes towards infinity. So can you guys go ahead and find that out for me? What is the value that it's approaching as it goes off towards infinity? So go ahead and give those two a try. I'll give you a, let's say, 5-minute timer on this one, okay? 5 minutes. See what you get in 5 minutes. See what you attempted in 5 minutes. That's the big one, right? If you don't know it, you at least attempt it, right? Because you're not just going to sit there for 5 minutes doing nothing. I hope you don't sit there for 5 minutes doing nothing. Hope you attempt it. Try those out. What is going on here? What's happening? 40 seconds. Oh God, gee, thought I'd be ready for that, but I wasn't. Oh my God, that was so loud. Ugh. All right, so, jeez. So, how many of you guys were able to get the first one? You know what? Yeah, how many of you guys were able to get the first one? Let's take a look. Let's take a look. A lot of blank boards, except for a couple of you guys. Oh, I only got like 4 answers. What's going on? Oh, there it goes. Oh, you guys are updating it now. Awesome, awesome, awesome. Okay, so a couple more answers in there. That's beautiful. That's beautiful. So let's talk about this, right? What is this thing doing as it goes off towards infinity? Now, I'm not asking you for what a horizontal asymptote is, by the way, right? I'm just asking you what is it approaching, right? So y equals 2 is perfectly fine. And you can actually say that the limit for this one doesn't exist if it goes off towards infinity, actually, right? It doesn't approach anything. It just approaches infinity or negative infinity is a possibility, right? But let's take a look at this one. So there's a couple things you can do, right? You could look at it graphically, right? See what it's doing there, right? Plug it into a graph and see what is it approaching and see if you can figure out what that number is, right? But then if you see it approaching something and you don't know what that number is and you're trying to guess it, it might not be super accurate, right? Numerically would probably be a better chance. So once you see it graphically, you're like, oh, it is approaching something. So then you can start plugging in numbers numerically. But then some of you guys might be struggling a little bit here numerically because of that sign, right? I know some of you guys are not that comfortable with trig functions and doing that numerically and seeing what's happening there. So that's another possibility you could do, though. You just plug that into a calculator and see what you get on the table as it goes off towards that. But then what happens if that doesn't work and we got to try this algebraically? That's one thing that we should take a look at here is understanding I didn't show you these properties for no reason, right? I show you these properties to hopefully see that you can apply them to different functions. And you'll look at this one and hopefully see that we can actually apply it to this function where you're like, I only see one function. It's 5x plus sine x over 3x. But I'm hoping you guys were able to spot this, right? You could actually rewrite this. And you could rewrite this at, instead of it being just 5x plus sine x over 3x, you can rewrite this as 5x over 3x plus sine x over 3x, right? I'm hoping you guys are able to see that. And you can say that, hey, this is one particular function, and then this is another particular function. And if I could find the limits as x goes towards infinity of each of these individual functions, right, then I can just add them together because that's what the property is stating, right? The property of these limits. If I just sum them together, I can get that value as well. So let's say I was calculating this out, and then I can say, well, then what is the limit, right, of x going towards infinity of just 5x over 3x plus the limit as x goes towards infinity of sine of x over 3x, right? This makes it a little bit easier when you see that because 5x over 3x, if we simplify that, that simply just comes out to be what? 5x over 3x just simply comes out to be 5 over 3. I hope you guys see that, right? It just comes out to be 5 over 3. And then if I take the limit as x goes towards infinity, it's still just going to be 5 over 3, right? That's all that is stating, that this guy right here, the limit of that, the x's cancel out, and you're just left with 5 over 3. And the function 5 over 3 itself is just constant. So if I go towards infinity, it's just going to equal to 5 over 3, okay? Now, when I'm looking at, let's say, this function over here, I'm trying to, oh, that infinity looks trippy. So I was looking at as x goes towards infinity of this function, right? This is where I'm going to have to do a little bit more combination of the two, right? I need to now look at sine of x over 3x, and I need to look at this either numerically or graphically on its own there. And this one I want to see as this limit goes off towards infinity of sine of x over 3x. So let's take a look at this numerically, right? And I start to think of numbers that are fairly large. So as I keep approaching this here, x is going to get larger and larger. So I could say like, oh, in the bottom, I'm going to end up with 3 times a fairly large number. Let's say like a million or a billion or whatever, right? This is just going to get off and go towards infinity. Yeah. But in the top, I have sine, right? And if you guys know what sine looks like, just the basic function of sine, right? It does this thing where it goes up and down. And it goes up and down forever, right? Now, will it ever go past 1 or go past -1 for a sine function? I hope you realize that its altitude is just 1, so it's just going to go, the largest this thing will ever get for the sine function, right? The largest it will ever get is 1, and the smallest it will ever get is -1, right? So I'm just going to say as it goes off towards infinity, it's either approaching 1 or it's approaching -1, meaning it's between -1 and 1, so it's fairly small as I go off towards infinity. So what this is going to be, what's going to be happening over here is it's going to be on the positive side, and then at some point it's going to be on the negative side, and the bottom is still going towards infinity. And I'm hoping you guys realize as I make that number larger and larger in the bottom, this thing's bound between 1 and -1, which means that this thing is going to slowly approach what? It's going to slowly approach 0 as this thing goes off towards infinity. So the limit as x approaches infinity of sine of x over 3x, right, as I look at it as it goes off towards infinity, right, it actually approaches 0. So this function right here approaches 0. And once I do those guys, I can just add those two together. So the limit as x goes towards infinity of 5x plus sine x all over 3x, this is just simply equal to 5 over 3. Weird, right? Now, I had questions in my other class. Well, how do I know that the limit as x goes towards infinity of this thing is going to approach 0? And I didn't know that. It's just something that you have to try to figure out based off the functions that they give you, right? Based off the functions that they give you. And you'll say, Nagmi, can't I just divide these two? And I could, but it doesn't help me too much if I were to divide it and calculate the limit of this one. Actually, if I did do that, you still come out with this result over here. The limit as x goes towards infinity of sine of x is still either going to be +1 or -1, but the bottom is still going to come out to be infinity. And you're still going to have to go through there and compare x 1 over infinity as it goes off. I'm sorry, guys. Hold on a second. There's a gigantic spider in here, and it's freaking me out just a little bit. I hate spiders. So give me 1 second. It's dead. Okay. Sorry about that. Yeah. Sorry. Creeps me out. All right. Ugh. Okay. So hopefully that makes sense, right? Of why that works, or how this approach works. If you're still a little confused on this, or a lot confused in some cases, don't freak out, right? Like I said, this is a weird thing to be looking at, but that's essentially what's going on, right? So let's do another one. Let's do another one. Let's do this one right here. I'm going to move this to the side so I have a little bit more space to write. By the way, if at any point you want to go back and look at my notes, right, just remember your notes are always posted on the homepage, right, on my Canvas page. So I just wanted to show this just in case you haven't been there to see it. Under notes right here, there's period 3. You just click on that, and it'll take you to the notes that I have right here on a OneNote page. So you can scroll through on today's notes. Today is the topic that we're doing is 1.2 limits at infinity. So you can go ahead and see that. All right. So if I ever go too fast and you are too shy to tell me that, which you should never be, but if you are, go on to Canvas so you can get onto the notes and you can see it from there. All right, let's take a look at this one. This one I can't split into 2 functions. I hope you can see that. I cannot split this because the plus sign's in the denominator, and denominators don't work that way where we can split them into 2. Right? If the addition is in the bottom. You can only do that if the addition is in the numerator, right? The addition's in the numerator. So back over here, I would say for this one, I'm looking at it as it goes off towards infinity. I do this I look at this idea of just what is it doing as it goes off towards infinity, right? What is this function doing? And it's the same concept as what we were looking at earlier. If I was looking at this as it approaches infinity, the sine of x function, right, it's just going up and down. So sine of x, it's approaching either 1 or -1. It never goes anywhere beyond that. It's the largest it can be is 1, the smallest it could be is -1, and it never does anything else after that. In the bottom, on the other hand, I'm going to have a fairly large number of infinity plus another large number of infinity, right? It's actually infinity squared plus infinity, which doesn't even matter of that square because it's still just a very, very big number, right? So if I look at this thing, I can say that this thing right now is approaching 0. And what I kind of wanted to show you from this one, and this one ended like abruptly quick, right? But I just wanted to show you when you deal with these limits and they're going off towards infinity, one technique, right? One algebraic technique, I should say, is to basically divide everything by x and see what it does there. Because when you do that, if you end up with a limit and you see it's approaching something, it doesn't even matter what that number is. If it's, as long as it's a number and it's over infinity, that's telling you that this thing is going to approach 0, right? And if you think about that, think about it. Think if it's the numbers like 100, even if it's 100 over infinity, the infinity part is going to beat it out every single time. It's going to be way larger than the other number, right? So if you have anything over infinity, it's approaching 0. But if you have it the other way around where it's infinity over something, that thing is approaching infinity. I don't know if that makes sense, but hopefully you can visualize that, right? If you have a number, like let's say it was 5 over infinity, it's still going to be approaching 0. If you had like 100 over infinity, it's still going to be approaching 0. So it doesn't matter as long as you can prove that what you're dealing with has a larger, it's going towards infinity faster in the denominator than it is in the numerator. So for example, here, let's say I have here the limit as x goes towards infinity of x over x squared, right? If I have the limit as x goes towards infinity of x over x squared, algebraically, you can kind of see that you can simplify x over x squared, and that just comes out to be 1 over x, right? And then you end up with this thing where you're comparing it, and you see like, oh, 1 over x is just the same thing as 1 over infinity, which means that it's approaching 0, okay? Or if you wanted to, let's say I had the limit as x goes towards infinity of x to the third over x to the fifth, right? Well, this one, same thing. If you simplify it, it becomes 1 over x squared. But again, I should say that equals 0. Again, though, as it goes off towards infinity, 1 over x squared is the same thing as 1 over infinity squared, or in other words, just 1 over infinity because it's going off towards infinity. I would still say that this is also approaching 0. I'll give you another example. I got 5 minutes. The limit as x approaches infinity of, let's say, x to the 30th over x to the 31st. Have you guys caught on to this yet? This is also going to be approaching 0. There's a pattern going on here that I hope you guys can see. And it actually links back to if you guys took pre-calculus, or even if your IM3 teacher taught you about horizontal asymptotes. There's a connection here with these limits as it goes off towards infinity and the idea of horizontal asymptotes, right? It's all circling back to that, and I hope you guys are seeing this. One property that you should have learned when you were learning about horizontal asymptotes is if you're dealing with a rational function, right? Would you guys agree that if the degree of the numerator is smaller than the degree of the denominator, then the end behavior for this thing, or the horizontal asymptote for this thing, is going to be equal to 0. You're going to have a horizontal asymptote at y equals 0. And no matter what, you can make it like x to the 30th and in the bottom x to the 50th, for example. You'll always end up with a horizontal asymptote at x equals 0, right? But it doesn't work if it's the other way around. So paying attention to the powers and the degrees of these numerators and denominators will actually help you with your limits as it goes off towards infinity as well, right? Now, how often are you going to do this? I have no idea. It's just a fact, and I don't want you to memorize it. I just want you to understand that, right? Like, it's a property that is, it could be useful, it might not be useful at all, right? So then another case is what happens if you're looking at the limit as x goes towards infinity, where the numerator has a higher power than the denominator. So for example, I've had x squared over x. Well, when you simplify that, you end up with just x over 1, and that's going to end up going off towards what? As x goes towards infinity, the function itself is also going off towards infinity. So the limit for this one doesn't exist. So things to keep in mind, right, is to look at the degree of your functions and seeing, and if you're dealing with infinity in particular, right? So if the denominator has a greater degree than the numerator, this thing's going to approach 0 most likely, right? If the degree of the denominator is greater than the degree of the numerator, right, for f of x, I hope you then realize then the limit as x goes towards infinity of f of x is going to approach 0. And it's a nice little technique that helps us out here. What I want you guys to think about for the next time we meet, right? This is if the degree in the denominator is greater than the degree in the numerator. Can you think about other cases then? What will happen? And I kind of showed that right here. This is for when the numerator is greater than the denominator. There's one more case left. And I want you guys to think about that last case before we call it a day here. Is, well, what's going to happen for that last case? What would be the limit of f of x as x approaches infinity for the last one? So this is if the denominator is greater than the numerator. This one is if the numerator is greater than the denominator. There's one more case that I want you to look at when you're dealing with degrees and these functions. You can take a look at the homework. You can attempt it. You won't be able to finish all of it because we have not gone over vertical asymptotes yet. But if you feel like you got that down, you can go ahead and try it. I'm at my time limit for today, so I'm going to wrap it up here. You can start your homework from 1.2 if you want, or you can just think about this question right here. And that's it for today, guys. Hopefully it wasn't too crazy. And if it was, stop by my office hours today. I'll be in here from 1 to 2 if you have any questions, okay? Other than that, guys, make sure you have a good day. I'll see you guys next week on Tuesday. You have no school on Monday. All right? Have a good day, guys. I'll see you guys later.